Hi guys, this is the video about tutorial 5, systematic organic chemistry. Let's look at question number 1. List the nucleophile and electrophile. List all nucleophile that you remember. So the definitions for nucleophile is a species, molecules, or ions with at least one lone pair of electrons. So anything with a lone pair of electrons, at least one, we can categorize them as a nucleophile. Examples of nucleophile here can be OH minus, because it has 3 lone pairs, okay, minimum 1 lone pairs. Number 2, it can be ammonia with a lone pairs. Number 3, it can be a cyanide with 2 lone pairs. All right. Number 4, even a chloride can be a nucleophile. Number 5, bromides, and number 6, iodides, because all this with lone pairs. Okay, now not necessarily for a nucleophile to be negatively charged, like ammonia. It's not negatively charged, but it has a lone pair, so we still call it as a nucleophile. All right, so these are the examples of nucleophile with lone pairs. Electrophile is something loves electrons, or itself is actually positive charge or partially positive charge. So usually electrophiles, the common one will be any acid, H+. It can be electrophile. Or number 2, it can be a structure, CBr, CH3Br, with the carbon as delta positive, Br as delta negative, and the carbon with delta positive as electrophile. All right. Number 3, it can be as simple as HBr, delta negative, delta positive. So the H here is an electrophile. Number 4, it can be even a non-polar molecules. Let's say, for example, I have bromine molecules. Because of a temporary dipole, you still can form delta positive, delta negative. So these delta positive act as a electrophile. All right. So nucleophile with lone pairs will always attack anything which is positive or lack of electrons. Basically, we can say nucleophile always attack electrophile. Electrophile love electrons. They always attack anything with electron rich, including nucleophile. All right. So electrophile attack nucleophile, or electrophile must able to attack, will be able to attack anything electron rich. Just example, alkenes with pi bonds, or alkyne with the triple bonds. So anything with extra electrons is susceptible to electrophilic attack. All right, so these are the examples of electrophile, nucleophile. And one more attackers, just for your informations, we learned that in the summary, we learned that in OL. One more attacker is actually radicals. So these are the 3 radicals, 3 attackers: radicals, nucleophile, and electrophile. These are the things that initiates a organic reactions. All right, without either one of them, without all this, no organic reactions can take place. All right. Now, another question here about substitutions of alkanes by radicals, or sometimes we call it as free radicals substitution. All right, so that's the name of the reaction mechanisms when alkanes react with halides or halogens under UV conditions. So for methanes and chlorine reacts together to give chloromethane and hydrogen chlorides. Let's say, look at A. Write a balance symbol equations for these reactions. So this is the reactions between methane, which is CH4, plus chlorine, Cl2, and then the products here, it states as chloromethane, so it will be CH3Cl, chloromethanes, and HCl, hydrogen chloride. Okay, and that will be the balance equations. Next, part B, explain the mechanism for this reaction using at least 4 steps. So you should include initiation, propagation, and termination. So we split it up. First one is always initiation, which involve the formations of free radicals. In this case, chlorine molecules involved. Under UV light, you will get 2 Cl radicals. Okay, to be more specific, the chlorine can be shown as Cl with a single covalent bonds, and then you break the bonds homolytically, half arrow to both directions. So you're getting your own valence electrons. That's how you get the 2 free radicals. Okay, always remember the definition for free radical is a species or an atoms with unpaired electrons. So the second step is propagation, in which the radicals attack the alkanes. In this case, the alkanes is methane. So CH4 reacts with one of the radicals. We should assume that the radicals in excess and the methane molecule is limiting reagent. All right, so you will get CH3 radicals after the Cl grab one hydrogen to form hydrogen chloride gas. All right, always remember radicals will actively looking for another electrons to pair it up so that they form a stable molecules. That's the first step. And these CH3 radicals form is going to attack any free chlorine gas. All right, to get CH3Cl, grab one of the Cl and the remaining Cl in turn becoming a radicals. All right, all these under homolytic fissions. Okay, this is just a dot, this is not the radicals. Right, let me erase that just in case you guys confused with that. Oops, why is it not working? It's fine. So that's not radicals, that's a dot. So these will be radicals, right? So why only two propagation steps? Because in this case, from the overall equations here, the products required will be CH3Cl, which we already obtained it, and HCl as a byproduct, which already obtained it as well. Also, the last step will be terminations. Okay, so termination is the combinations of any two radicals from the propagation steps. So in this case, I can see Cl radicals, CH3 radicals again, right, and Cl radicals again. So maybe you can combinations of CH3 radicals plus Cl radicals to get CH3Cl, which is the product, or even the double of both. So it can be two Cl radicals combined to get chlorine gas, or two CH3 radicals combined to get C2H6, which is an ethane. So these are the possible products during termination steps. That's A and B. All right. So the next step will be C. Part C. Now, part C, what are the essential conditions for the initiation step? Obviously, you need UV light. Okay, UV radiations provide enough energies to break a covalent bonds between all the halogens. And bonds energy between halogens are actually slightly weaker compared to the rest of the covalent bonds. So D will be, this is UV light. For D, draw a molecule of chloromethane, label the bond angle. So they want it to draw in a shape. So CH3Cl, central atoms carbon, C, and then 1, 2, 3, 4, right? So you have 3 hydrogens and 1 Cl. Now the Cl can be anywhere, the hydrogen can be anywhere because it's a tetrahedral shape. So this is a tetrahedral. And the bond angles between each bonding pair will be the same, 109.5 degrees, which we have learned in chemical bondings. All right, so this is what they want to draw it. And always remember, in a 3D form, it's supposed to include this triangle and then the Vegas line. That indicates the 3D molecules. The triangle is pointing towards yourself. When you look at the molecules, the Vegas line is actually pointing backward, pointing away from the central carbons. All right, so this will be question number 1 about substitutions of radicals. Okay, question 2 is more or less the same. It's just that they change it into ethane and bromine. All right, so number 1A, work out the equations. So ethane is C2H6, or you may write it as CH3CH3, up to you. And then mix with bromine, Br2, and then you're going to get bromoethane, which is C2H5Br, one of the H substituted, and then you get HBr. So that's the balance overall equations. For B, work out the mechanism again. So we have initiation. Okay, again, bromine molecules is going to break into radicals, 2 Br radicals under UV lights. All right, and propagations. So propagation step, you work until you get the final products required, which is C2H5Br. So, which is 2 steps. Number one, we have C2H6 plus Br radicals. So what do you get? Br radicals grab a hydrogen from it to get HBr. That's one of them. And then the remaining will be C2H5 radicals. So they take turns to become radicals. These C2H5 radicals is going to attack any free bromine molecules, because under these conditions, even there is a UV light, the bromine is in excess. Therefore, we don't expect 100% of bromine converted into radicals, right? So there's still some free moving bromine molecules which are attacked by these C2H5 radicals, and then you grab the Br, you get C2H5Br stable, and in turn produce another free radicals of bromine. So we got what we want. The product, stop propagations, and last one, the termination step, will be the combinations of any possible radicals. Let's say, for example, C2H5, I have two of it. All right, I may get C4H10. I will get a butane. This is one of the possible products. You see that? Any possible radicals can combine together, even by itself. Like C2H5, although it appears as once here, only one C2H5, but all these reactions is happening concurrently. So here maybe one C2H6 involved, but at the same time another C2H6 molecules attacked by another bromine molecules. So bromine radicals. So we expect more than one reactions taking place. Okay, so it's possible to get two C2H5 radicals. Okay, or we have two Br radicals to get bromine, Br2. Okay, always remember terminations will always produce a stable product. All right, that's how you terminate the whole radicals reactions, which is a chain reactions without any UV light. So termination reactions only happen in a dark room. So as long as UV light is present, terminations won't happen. All right, so that's A and B, and let's move on to C. Again, the same thing, essential. What is needed for the reaction to take place? UV light. Okay, UV radiations. Draw the full structure formula of two RA organic products that might form in these reactions. Now, when they ask for other organic products, which is the one, what are the main products here? Bromomethane and hydrogen bromide. So you should suggest your answer other than these two. So just now, we work out the termination steps, right? So maybe one of them, C4H10, right? They want structure formula, so basically it's CH3, CH2, CH2, CH3. Okay, that's one of it. And what else could be the product of this terminations? So what are the radicals again? I can have two C2H5 radicals. These are the possible radicals. I can have Br radicals. All right. And then I can have two C2Br. Yeah, why not? We have this Br radicals. Two Br radicals, you get bromine. Okay, but then this bromine 2 is not considered as an organic product. See, they want organic products. Br2 is just an inorganic product. Organic product must compose of CH as a minimum. So in this case, what else you can get? Like I said, concurrently they might have another set of reactions ongoing, another set of C2H5 reactions ongoing. So it's possible to get C2H5 radicals, but three of them. I have three radicals of C2H5. So what do you get? Three radicals of C2H5, then you get C6H15. Wait, that doesn't make sense. No. So I don't think this happened. Not C2H5 three radicals. Maybe we can have this. C2H5Br as one of the product, and if the propagation step goes on, then these may change. Let's say, for example, it reacts with bromine radicals again, then you may get C2H4Br radicals plus HBr, right? So this is one of the possible propagation step where we have another new radicals here. So if two of these radicals combine, let's say I have C2H4Br radicals combined with Br radicals, then I shall get C2H4Br2. Yep, that's another product, possible organic products. You see that? So this is another organic product, this is another one, so they want two, that's enough. All right, any other possibility, if you were able to work it out, just clarify with me, because the more propagation step you have, the more possible products you can made of. Organic products, I'm talking about organic products, so you must involve C and H. Okay, so that will be question 2 for free radicals. Question 3, complete the following equation: C3H7 dot plus chlorine. So this is one, they want you to estimate the product's form. In this case, when you have a radical plus chlorine, obviously C3H7 radicals grab one Cl, leaving behind another Cl radicals. All right, and for this C3H7 radical plus radical, this is termination step, so we'll have C6H14. All right, you get a hexane. And the third one is C3H7 radical Br, same thing, C3H7 grab one Br, leaving behind another Br radicals. And bromine changing into something. Since this is under free radical substitutions, I'm expecting it to change into two Br radicals. All right, I should put the UV light here. And C2H5Cl plus Cl radicals. Again, the Cl radicals is attacking the H. See that? One of the byproducts is HCl. So the remaining product will be C2H4, lack of one hydrogen, and then Cl, but then this is a radical. All right. And for part B, bromoethane can be prepared by substitutions of hydrogen using bromine. What are the two main problems with using this method? So if you want to produce bromoethane, which is C2H5Br, okay, the method will be this: free radical substitutions by reacting ethane with bromine, right? So what are the two main problems because of radicals? The formations of radicals in these reactions can cause depletions of ozone layer, because ozone layer is O3. Okay, if in encounter with any radicals, any free radicals, in this case if you're using bromine, there might be a free radicals of bromine here, then what's the main product when the radicals attack the ozone will be you're producing oxygens and then O radicals. You're breaking down the ozone molecules. So if this continues, then the whole ozone layer will be depleted soon. All right, that's one of it. And then what else is, you need a strong UV light, and you need to have consistent UV lights, otherwise these reactions won't happen. So they want, another main problem will be, what if the UV light is inconsistent, and that will actually affect the overall percentage yield of the products of the bromoethane. You may not get 100% of bromoethane because inconsistent supply of UV light, although UV light is everywhere, but just that the intensity of the UV radiations need to be consistent, because it's all about energy breaking of covalent bonds. If the UV light provided, or the UV light available, is not strong enough, the intensity is not high enough to break a covalent bonds, no free radical form, no initiations, therefore no propagations. Okay, so it's impossible to get a product. So this will be another main problem for the method. Okay, next we look at electrophilic additions of alkenes. So alkanes, basically we're done. In terms of alkenes, still remember alkene has a double bond or a pi bonds, and this indicates that alkenes is electron rich compounds which is susceptible to electrophilic attack. Electrophile loves electrons, right? So in this case, it's based on electrophilic additions of alkenes. So ethenes react with bromine to give 1,2-dibromoethane. Ethene is C2H4 with double bonds. 1,2-dibromoethane is when 2Br has been added to the structure of ethene. No more double bonds, so it's ethane now as the only product. All right, addition will always give you single product. The mechanism for the reactions is electrophilic additions and involve heterolytic fissions. The bromine molecule behave as electrophiles in these reactions. By what mechanism does bromine react with ethane? So, I guess here's some error. It shouldn't be ethane, it should be ethene. Okay, but if you have worked out the mechanism with ethane, go ahead, because that will be good for to refresh your memory about free radical substitution. What if I change it into ethane? What mechanism is that? So it's stated clearly on top. It's actually electrophilic addition. Okay, write a balance equation for these reactions. So I have C double bond C, the rest all H, C2H4, which I'm going to react with bromines, Br2, and then you get C, Br, Br, H, 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 H. Now you may ask, can I write an equations like that? Yes, you may write it in a display form. You may write it in a structure form, but in this case, I would not encourage you to write it in a molecular form, like you just put it as C2H4, so that we can't see it, the presence of double bonds. We can't see the main changes in that. So it's good to not show it in a molecular formula. Structural display will be good. All right. So you can write it out. Yes, this is still a balanced equations anyway. So AB done. Part C. Bond breaks in this reaction. So what type of bond breaking is involved? Since it is based on the passage, and the answer should be given there. So answer is heterolytic fissions, because electrophilic addition is due to the presence of electrophile, not the UV light. All right. So for part D, show the mechanisms of reaction as fully as you can using curly arrows. Now I mentioned that in the summary, saying that when you draw or when you construct a reaction mechanisms, please make sure that you include all the little details like dipole, delta positive, delta negative. You need the lone pairs so that it makes sense. Otherwise, you won't be able to differentiate whether it is an electrophile or a nucleophile, and why is it attacking each other. All right, curly arrow is the most important because it indicates the movement of a pair of electrons. So always remember, curly arrow in this case is due to the movement of a pair of electrons. So that is a full arrow. Okay, half arrow only exists when it is homolytic fission during initiations. Okay, so let's show part D. So this is a reaction between ethene. Again, I'm showing the ethane formula. Plus with bromine. So I'll show in this form so that I can show delta negative, delta positive. I can show clearly where is the electrophile. And then I'm going to change the color to show the curly arrow. Again, the electrophile of Br positive is attacking the double bonds. But then the curly arrow is always from the pi bonds, from electrons to positive, always. Okay, and then first curly arrow done, and next curly arrow is when this double bond is attacking the Br, the bond between Br molecules is going to break heterolytically as well to the delta negative bromine. So two curly arrow here, resulting in another two products. So what will be the products here? C, single bond, no longer double. The pi bond has been used to attack the Br. So he attached to one of the Br, and the carbon here in turn become a carbocation. Right? And then don't forget, see this? The delta negative Br is receiving a pair of electrons, so you will get Br minus with a lone pair. Okay? And now you have a positive and a lone pair, so this is a nucleophile attack, the positive carbon, and then you will get the final products as C, C, the rest remain the same, H, 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 1 Br, 2 Br. So that's electrophilic additions. Right? So curly arrow, each of the curly arrow will give you 1 marks. And then the dipoles and the lone pair, if you state it clearly, dipoles and lone pairs, you will get 1 mark. And then the structure of the final product, will give you another mark. So it's about 5 marks for this electrophilic addition. That's the answer for D. Now look at E. Which substance behave here as an electrophile? Explain what is meant by the term electrophile. So which species here, which substance as an electrophile? Obviously the bromine. And the term electrophile meaning that it is a substance, a compound, or molecules that lack of electrons. Okay, it is a compound that lack of electron, like this case, delta positive, right? It's lacking of electron because the electron pair from the bond here is moving towards another Br. Alright, so yep, basically the definition of electrophile. Okay, next one is about eliminations. So elimination is removing something from the molecules to form an alkene. So the ultimate goal here is to form alkenes, double bonds, right? So let's look at this compound. Now this obviously is an alcohol. Now first, to eliminate it, or they call it as dehydration, to be exact. Why? Because the one that we're going to remove is actually water molecules. So there's another name for it. If you are eliminating water, you may call it as dehydration, but nothing wrong if you call it as eliminations, because that's the general name for the whole reactions. So in this case, I have an alcohol here, right? So I'm going to remove water from it to get the double bonds. First thing what we're going to do is remove the OH. Another one, we should remove another H, right? H2O. So where does the H come from? It should be from the adjacent carbon. Now the OH is from carbon A, right? The alpha carbon, we call that. Okay, the carbon attached to the functional group OH, we call it as alpha carbon. So we remove the OH from the alpha carbon. Then another H should be from the beta, which is the adjacent carbon. How many adjacent carbon do we have here in this structure? We have here and here. And both are the same because it's symmetrical. So if they are symmetrical, so it doesn't matter which carbon you're removing the hydrogens from. So either way will give you the same alkenes, right? So let's say I'm removing the hydrogen from here, CH2, 3 becomes CH2, so you will get CH2 here. Double bond now, CH remain the same, CH3 remain the same. Of course, the OH is gone, plus H2O as a byproduct. So this is the alkenes. If I remove from another CH3, it will result in the same product, because if you flip the molecules, they are exactly the same. So how many isomeric alkenes, how many different structure of alkenes could be obtained from this? Your answer is 1, right? Unless you have asymmetrical structure. You can remove the hydrogen from different compounds and then lead you to a different structure, then yes, you may get more than 1 alkenes. Let's look at the next one. So how many isomeric alkenes could be obtained from this compound by eliminations of HCl? So you're going to remove HCl. Of course, the first one, we're going to remove the Cl. And then this is the alpha carbon, because alpha carbon always attached to the functional group. In this case is the Cl. So adjacent carbon, the one next to the alpha, will be this, this, and this. Make sense? So I label it as A, B, C. So I remove the Cl. Next, I'm going to remove a hydrogen from A, which is here. Then the resulting alkenes will be CH3, CH, no more, double bond C, CH3, CH2, CH3. That's one of it, right? If I'm removing from B, then the structure will be CH2 on top, double bond will be here, alpha carbon, CH2, CH3, the rest CH2, CH3 remain the same, right? This is another alkenes. If I'm removing from C, look at that, A and C, they are the same, symmetrical. Look at the whole structure. Of course, not just look at the CH2. If you look at it, on the left hand side is CH3, CH2. On the right hand side is CH3, CH2 as well. So there's no difference if you remove hydrogen from either one of them. So A and C will give you the same structure here. Therefore, the total isomeric alkenes formed in this case will be 2. Right? So next, how many isomeric alkenes could be obtained by the dehydrations of this alcohol? Now the structure given here, again, I'm removing the OH. Next, I'm going to remove from the adjacent carbon for the hydrogen. So I have to label them. This is the alpha, adjacent, adjacent, adjacent. Right? So, are all 3 different? Let's check. A, B, C. Are they all different? This is a CH with 2 CH3. The B is a CH3. That's it. The C is a CH2 with a CH3. A, B, C, all different. So you should expect to get 3 different alkenes. So straight away, answer is 3. So if you're familiar with this method, first remove the OH or the Cl or the Br, and then the hydrogen should be from the adjacents, right? Identify all the possible adjacent carbon and make sure all the carbons are different. If it is the same, then they will only give you 1, right? So if you have 3 different carbons, 3 different adjacent carbon, you should get 3 different alkenes. If you have 2 different adjacent carbon, then 2 different alkenes. Simple, right? This one is kind of like a multiple choice, but then you must know the theory of eliminations. Now, which of the above compounds could be starting materials for the synthesis of pent-1-ene? Okay, so I'm going to eliminate or dehydrate A, B, C, D, E, F, all these compounds. Okay, eliminations. Which one will result in pent-1-ene? Okay, let's check it out. So pent-1-ene should be 5 carbons as the longest chain, and then the double bond should be at the first carbon or at the terminal. So in this case, for A, remove the OH and remove another H from where? Adjacent here. If you remove from either one of these, the double bond will not actually at the terminal, right? So the most it can be 1, 2, 3, 4, 5 pent-2-ene. The most is pent-2-ene. You can't get pent-1-ene. So A is out. Next, Cl adjacent here. Yep, the double bond is here because they only have 1 adjacent and the double bond must be here. So once you get this double bond, 1, 2, 3, 4, 5 pent-1-ene, because it starts from the double bond 1, 2, 3, 4, 5. So this will give you pent-1-ene. B is a yes. C, remove OH, remove adjacent, either one. If you remove from here, you get a double bond at the first carbon, but only 4 carbons here. So these will not give you pent-1-ene. Maybe built-1-ene is a yes. So C is out. Part D, OH, remove here, double bond here, 1, 2, 3, 4, 5. Yes, it is. E, remove this double bond here. If I remove from here, so 1, 2, 3, 4, 5 pent-1-ene is a yes. And Cl adjacent is just these 2. You can't get 1-ene, right? It shouldn't be at in the middle. So this is a no. So answer is just B, D, E. So here. All right. So I guess that's it for the tutorial questions. I've added additional question if you're aware. These eliminations reaction, all this are additional questions I've added in so that you can have a clear picture on what is that. And about the oxidations of alkenes, make sure you revise that. I have done it. I've recorded it as well just now during the class. And also the all the mechanisms. So let me do a summary, a quick summary here. What are the mechanisms you need to pay attention? First one is electrophilic addition. All right, that's the first mechanism. Make sure you know in and out thoroughly about these things. Number 2, you must know the mechanism for eliminations. Elimination, remember, including dehydrations, right? And then the third one is not mechanism, but you must know what are the steps for the oxidations of alkenes. Yeah, oxidation of alkenes, if it is hot concentrated, still remember you're going to break the double bond and split it into 2, add double bond O to each, identify whether it's alkene or aldehyde or ketones. If it is a ketone, it stays as ketones. If it is an aldehyde, it will further oxidize into carboxylic acid. So these are the things that you need to pay attention for oxidations of an alkenes. Alright, I guess that's it for the video for this tutorial. Anything, just let me know in the next class. Thank you.